Okay, before I start my talk, I want to advertise a conference that will be happening next year. So it's New Geometric Methods in the Langlands program in Singapore from August 23 to September 10 of 2027. The details will be out soon. You'll find them in either my or David's or Xinwen's or Eva's website, perhaps for some. It should be a lot of fun. It should talk about similar subjects, but also other connections with kind of neighboring areas. So yeah. Okay, after that short commercial, let's go back to the talk. So now I want to tell you, okay, now I just told you how to construct a functor from one side to the other. The next thing I need to tell you is why it's an equivalence, and I will not be able to tell you everything that has to be said about this, but I'm hoping to give you a little bit of ideas of what kind of ingredients go into. So the name of the game is that we actually, on both sides, we have very nice, I guess in this conference, sorry, I started doing the same thing, writing very big words. We have nice semi-orthogonal decompositions on both sides, and in Bun G, we can stratify by classifying stacks. Isoc is also stratified by classifying stacks, and all the categories glued out of these pieces, right? And of course, we believe that like B corresponds to B somehow, and we just need to understand why they glue in the same way, right? So, okay, let me try to capture. So I'm going to consider convex BG to be the following set, or actually I want to think of it as a partial order. So B is the subsets of BG such that B is finite, and it is convex. So that means that it contains an interval whenever it contains two elements. Okay? And you can think of this as a set or as a partial order or as a category, whatever taste you like. But the point is, every time you have B1 inside of B2, you get an inclusion functor, an inclusion map that I'm going to call JB1, B2 from 1GB1 to 1GB2. But you also get a similar one, B1 inside of B2. And this one I want to call IB1, B2. Okay? And the reversal of topologies tells you that whenever the map on the left is a closed immersion, then this one is an open immersion, and vice versa. Right? So actually, to tell you why this functor is an equivalence, it will be helpful for me to tell you more properties about this functor. So actually, this functor intertwines the following operations. And showing that the intertwining of the operations is a way of saying that the functor is compatible with semi-orthogonal decompositions in a way that I'm going to explain. But first, let me kind of tell you which operations get intertwined. So maybe, I don't know, maybe I can put this as a theorem that this happens. But it's a theorem, but it's also part of the proof. Okay, I told you that maps in Isoc are called I, and maps on Bun G are called J. So whenever you have I, you have a lower Schritt functor, and you also have an upper star functor. And this lower Schritt functor always has an upper Schritt functor, and this upper star functor always has a right adjoint, which is a lower star functor. But in the schematic world, actually, by design, upper Schritt and lower star are always continuous. And in particular, they admit an extra right adjoint. So this has a lower flat functor, and this has an upper sharp functor. And this upper sharp functor was also part of Xinwen's talk, right? When he discussed the exceptional T structure on Isoc, this upper sharp functor appears. And okay, it's something you have to get used to. So what does this correspond on Bun G? So this is on Isoc world. And what turns out to be true is that this lower strict functor becomes a lower sharp functor on Bun G. And what is this lower sharp functor? It is defined as the left adjoint of an upper star functor, and this upper star functor has a right adjoint. And similarly, what will correspond on this side is this upper flat functor corresponds to this lower strict functor, corresponds to this J upper strict. And actually, this matching is also the thing that is going to tell us that T exactness holds. Because T exactness maybe I don't want to talk about T exactness that much, but maybe the only thing that I want to say is actually the intertwining of these functors is the ingredient that gives us T exactness essentially for free. Okay, so I told you that this guy intertwines this, and maybe I actually want to be more precise. So the point is we have BG indexed semi-orthogonal decomposition on Isoc. Which I want to capture as a functor from correspondences on these convex sets to link at lambda. And what does this do? On some particular B, this is just sheaf shriek of Isoc GB. And if I give you a correspondence, then this is going to be IWU goes to lower shriek, composed with upper star. WB. So you pull back and you push. So this is a very natural semi-orthogonal decomposition on Isoc. But maybe I want to emphasize this is BG indexed. This is the natural partial order of Isoc. So this one kind of respects the topology. And if we want to make semi-orthogonal decompositions match, well, you have a semi-orthogonal decomposition also on Bun G, but it's actually BG up indexed, right? So somehow we need to also get a BG indexed semi-orthogonal decomposition, and there is such. And so there is an exceptional semi-orthogonal decomposition on Bun G that again ranges over this correspondence of convex to link at lambda. And okay, this part is easy to guess. This should just be D et al. Upon GB. But on morphisms, maybe it's a bit more exotic. And this will actually be the functor JW sharp composed with J flat WB. And essentially, we play the same trick that Xinwen was alluding to in his talk, that once you have like some perverse T structure or semi-orthogonal decomposition, you can pass to adjoints. And I guess usually in Bun G, you have a semi-orthogonal decomposition with respect to pulling back and pushing, like shriek pushing, but we can take that one and like pass to left adjoints. And of course, there is this process that you have to go through of showing that the left adjoints exist, but they do. And actually, this was already exploited with great success in the work of Schulze. And I guess maybe some of you are already very familiar with the JB sharp functor involving the MB charts. But it exists actually for any strata. Like for any map of strata, you will have like sharps and flats. And well, they have actually very nice formula. What is JW sharp? If you believe in this table, what is sharp corresponds to streak and flat corresponds to star. And maybe I told you that I already have this guy. So essentially I have this guy. If I want to get lower streak out of lower star, I just take duality, right? I can do Verdier duality to get the other guy. But Verdier duality for Isoc, well, we haven't shown this, but should correspond to Bernstein-Seliwinski duality on Bun G. So we just take that to be our definition. So this guy is the index tension of doing this. And you justify that this is an adjoint, and then you don't have to worry about anything else, because if adjoints exist, they're unique. Okay, so now that I have introduced some of this notation, then I can write a proposition. So this functor promotes to an equivalence of functors. In particular, if I have any of these convex guys, I will have a version of this functor relating shape shriek Isoc GB and D Bun G. And I like this presentation because I actually don't really want to tell you what exactly this functor does, because it involves some very kind of maybe let me just say, you can apply this to the convex set B inside of this. And there will be a functor from sheep shriek Isoc G B and D et al. Bun G B. And you can ask, what is this functor? This is an equivalence, but there's many ways that you can like take representations of GB and find equivalence with itself. And we actually don't know what we're twisting by. And we prefer to leave it inexplicit. We know enough to know that this is T-exact equivalence. But a priori, there might show up a magical twist, which we expect to be trivial. But okay, now I told you what I mean by intertwining, right? So I shriek apply pitch will be the same thing as pitch of that version of the strata, and then apply J sharp. And this way I don't have to worry too much about whether I have to put extra twists. Okay, so I told you the name of the game was to use semi-orthogonal decompositions. So here's a criterion. So pitch will be an equivalence. So pitch is an equivalence. So what do we have to verify? I want to verify that IB shriek of sheep shriek Isoc GV is inside JB sharp of D Bun GB. And for every B in this convex, for every convex set and B in B minimal, or you can think of it closed point if you're thinking in the Isoc topology, then I need to tell you why the following is true.
Ian, Alexander's confused by the terminology pitch.
Just this guy. Sorry, this is a pitchfork. Okay. Sorry. I take this and I take lower star, and I can take Isoc of B minus the point, and I need to tell you that, I need to justify for you that this is inside of this.
Sorry, this wild string, the superscript, I mean subscript, what is this? IV slash bracket curly B star?
This?
Yeah.
So I took a convex set, and I took a minimal element in it. Then I take B minus it. So this is an open subset. And then I can go from the open subset to the other set. So maybe it's like here, one of this. So if I have two convex subsets, there's always an I function from one to the other. And yes, I guess I agree it's very cumbersome to look at this. Maybe.
We're lower starting from B with the point deleted.
Yeah.
Okay, thanks.
Maybe this makes it a bit better.
Yeah.
So I guess, yeah, and finally, third thing we need is that PHP to this is an equivalence. Okay, so essentially, the first thing is telling us we need to intertwine lower streak with sharp, which is this one over here. And the second one tells us that we need to intertwine lower star with lower streak, which is this column over here. But it tells us that it is enough to not identify it all the time, but actually just once you take B to be a minimal element. Okay, so this is some inductive process that allows you to not prove the intertwining all the way, but kind of like just the intertwining inductively, like by removing like one point at a time, right? And finally, we're asking that on filtered pieces, it's an equivalence. So this is a very formal statement, and yeah, it essentially follows formally. But this is roughly the strategy that we are going to try to follow.
So what's the logical relationship between this and the proposition above it?
This?
Yeah.
Okay, so the logical connection is if this functor pitch satisfies these three properties, then it is an equivalence and automatically promotes uniquely to an equivalence of functors of this type. So you get all of the intertwinings for free as well. Okay, and the point is this is literally all formal. It's painful and formal, but it's actually just formal with playing with semi-orthogonal decompositions.
Ian, I don't know if you haven't actually defined pitch B yet.
Yeah. So, okay, Linus wants to bring some points we discussed, but so yes, as it turns out, the moment this condition holds, you can make sense of like what would be. I mean, I told you that there's this guy, and for every convex subset, you're allowed to kind of write a version of it. And this actually is true as long as this condition already holds. And It's because you're passing, somehow this is giving you some filtration, like you can filter both categories, and then this allows you to define on every B what actually happened. But I don't want to like really go into that part and just assume this makes sense. Okay, so now it's where maybe hopefully we get more fun, because I'm going to start telling you how we get A, B, and C. Okay, A. In A, we see some geometry. So let me recall the theorem with Ivanov and Zillinger. We have a diagram with Cartesian squares. And let me draw the diagram. So we have Bun G Mare. We have the special Newton polygon map. We have the generic Newton polygon map. And then we have this joint union of this. And the Cartesian square part comes here. You have B and BG. And what appears here are the Phi-Schulze charts. Maybe this map is QB, and this map is, maybe call me pi B. Right, and roughly this is saying that the Phi-Schulze charts have another interpretation in terms of the geometry of Bun G Mare. So this is the locus in Bun G Mare in which you imposed that the generic Newton polygon is constant for a fixed B. And you can also build a different space that I like to call TB, where you take Bun G Mare and you ask now that the special Newton polygon is equal to B. And maybe the picture I like to draw is maybe when G is GL2. Maybe we look at, maybe, let's say SL2. You have some axis Bun G, and you have some axis Isoc G. And here, there's one basic stratum, 1, minus 1, then you have 2, minus 2. You have 3, minus 3. But because you have the reversal of topologies on the Isoc axis, things get reversed. So here you have dots. Here you have 1, minus 1. You have 2, minus 2. And you have 3, minus 3. You have dots this way, dots this way. And here this has 3 non-analytic points. Maybe like this. And over here you have a bunch more of strata. But somehow, if you only look at this piece of the diagram, you have these 9 points where oh, sorry. I think I did something wrong. Okay. Oh, you get the picture. Yeah, too many. Okay. Okay. So I guess if you fix the, ooh. Okay, if you fix the generic Newton polygon, then you're looking at this, and this is an MB. Or if you decide to fix a special Newton polygon, then you'll get this infinite tower going this way that still only has one non-analytic point. Okay, and actually the secret between A, B, and C is related to this geometry. So what I want to say is why we can control A is precisely because MB happens, and I'll go and do one computation for you explaining how A follows from realizing that this generic Newton polygon is essentially MB. And B will actually eventually follow from studying this TB, I don't know if we can call them TB charts, but TB objects, TB spaces. So,
Is there a reason your picture stopped there and didn't go through the basic point?
it has the basic point. The basic point is, so this, in blue, this is the basic point on Isoc and the basic point in Bun G. Thanks. Yeah. My bad. Okay. So let's go and do a computation to show why A holds. MB, so MB should be given by this formula, that the generic Newton polygon is constant or fixed. And in this drawing, you have this Bun G mirror object, and it has a gamma map towards here, and it has a sigma map towards here. And the geometry of Isoc is just a line. And so if you fix a B, like if you fix this B, then MB will be this.
Yeah, but that's the but is that the definition or the theorem? But the theorem is saying you have this partition diagram, right?
Right.
So you cannot define MB to be this primary.
MB has its own independent definition, given in FACT-Schulze. And the theorem is that when you take this Cartesian diagram, like when you base change by this map, then you get this unions of MBs.
It's a moduli space of certain parabolic reduction.
Okay, so now I want to do the computation proving A. And okay, unfortunately I will start with the naive computation, because I gave you a very ugly functor, right? And I really don't want to compute with that one. So let's do the naive computation. So what is A? A is about intertwining IB lower streak with JB lower sharp. So I have this. Then the naive computation would tell me that this functor should be given by sigma streak, gamma star, analytifying IB streak. Then I can use that C star is a very general natural transformation of six functor formalisms to exchange C star with IB lower streak. So this follows from the six functor formalism, and I have this. Then I want to compute I want to commute this lower streak, and maybe I need to label an extra map. So maybe this map I call KB. So I have a IB, a JB, and a KB now. So okay, this tells me that this is the same thing as sigma shriek, KB lower shriek, and I was calling this map QB, QB upper star, C star. And then I can just compose, because I have KB lower shriek, sigma lower shriek, that's the same thing as pi B lower shriek. Right? But it doesn't matter what analytification is doing to this. This is going to land inside of J lower sharp of the Bun GB, because JB sharp up to twist is defined as pulling back to MB and then doing lower shriek. And here I'm free to say up to twist, because the up to twist is hidden by this functor pitch B that I was always talking about. So I kind of prefer to never care about the twist and figure it out later. And so this argument already does this for me. Okay, so this computation was very easy. It was essentially proper base change once you have this geometric statement, right? So because I'm going to do a much harder computation, and this one is also going to be a naive computation, let me give you a non-naive version of this computation. So non-naive version. But this is, again, a non-naive version of the easy computation. So, well, I guess this pitch functor was very non-explicit because it was taken as a colimit of functors that maybe we can make explicit. So we have to go back to explicit land at some point. So let me draw this. I have Bun G mer, and I have a map to Isoc G diamond, and I have Stuka I big diamond, and I have maybe Stuka bounded by W I diamond, and finally I have some Stuka IW inside of this. And I'm going to do this one not for all W. So I'm actually, there is this very cool theorem of Shuhuahe that puts in bijection BG with something that's called BW straight. So there are the so-called straight elements inside of this tells me that for every B that I pick, I can find some WB. So I guess these straight elements also already appeared in Xinwen's lecture. So I have this, maybe I'll only do it for WB. And for the magic thing about this is that this strata is actually very easy to understand. Stuka IW, this is essentially going to be point modulo some Iwahori, and this is going to be some Iwahori inside of GBF. And if I take this diagram and pull it by point modulo Iwahori, what I'm going to get over here is just going to be m bit tilde modulo this Iwahori B. And over here, I will get I will not be able to tell you too much about the combinatorics of this part of my mind, but there are these so-called straight elements. They're minimal, okay, minimal length in the same sigma conjugacy class. Yeah.
Then why can you reduce to only consider these stuff?
I'm about to say that. But okay, let me finish drawing this diagram. So here you have Stuka analytic bounded by WB, I, and this is now an open immersion, open. And finally here you have all of analytic Stukas. And all of these are Cartesian diagrams. So what is the point? IB lower shriek of sheaf Isoc B is generated under colimits by NTWB streak of sheaves on this Stukas bounded by W. Right? So this is just a fact that happens for Isoc. The whole category can be generated under colimits by all of these images where maybe this map NTW is this one over here. What this tells me is that if I want to compute under my functor pitch of where does pitch land when I apply it to this category, it suffices to do it of objects that are coming from here, right? But objects that are coming from here already factor through this guy, right? If I want to do a lower streak all the way to Isoc, then that's a lower streak first to this kind of closed bounded piece, and then like, you know, you lower streak further. But this, so that means that, but yeah, my functor was defined as a colimit of functors that are defined over a bounded piece, and this is already a bounded piece. So what I have to do is do lower streak over here, pull it, and do lower streak all the way to Bun G. So then I will have some representation here. I pull it to MB tilde modulo the Wahori, and I go all the way to Bun G. And this does land on the JB sharp category. So this is how you would translate this naive proof into a non-naive one. Okay. So there's another fact that I'm going to need. I told you that once I have A, I start getting this pitch B functors. And actually, one can write very explicitly what the pitch B functor would look like right away. And this is the following formula. So formula for pitch B. Well, you have to play the same game. You will have Isoc GB, and you will have another correspondence, Bun G mer B, and then you will have a gamma B and a sigma B, and you have a Bun G B. And here, maybe the important part is that Bun G mer B, well, it is what it has to be. You pull, in Bun G mer, you cut out exactly by the conditions that are imposed to you in Bun G and on Isoc. And essentially, you will get this, the naive version of this functor is again C star, gamma B star, sigma B streak. And of course, there will be a non-naive version where you have to range over bounded pieces and the sigma compatible with ones and taking colimit of this thing and blah, blah, blah. But this formula already gives us why C, the statement in our criterion, should be true. We need to show that on graded pieces this is an equivalence, but we can actually give a very explicit formula for those graded pieces, because then what we're doing is we are fixing the special Newton polygon. So we're looking at some TB, but we're also fixing generic Newton polygon, and actually we're fixing the same one, right? And we always have the inequality gamma larger or equal than sigma. So the generic Newton polygon in the geometry of Bun G mer is always larger or equal than the special Newton polygon. And in particular, it tells you that if you force gamma to be B and sigma, well, it will tell you that actually, okay, maybe let me say it this way. If you study the geometry of Bun G mer, you realize that on the strata in which the generic Newton polygon and special Newton polygon agree, you only get the non-analytic points. And so in this case, the diagram looks like this. Bun G mer, sigma equal gamma equal B is actually just point modulo GBF. And okay, Isoc GB we know that is just the point modulo GBF. And here you get Bun GB, which is the point modulo the diamond where you also have a unipotent radical, right? So this tells us that pitch B comes from just pulling back and Schrick pushing forward. And actually in this process of pulling back and Schrick pushing forward, you'll see a twist, right? And that's actually one way you could try to compute the twist on this part of the story. Another twist in this part of the story comes from the beginning of, the end of my last talk, where I, maybe not so, end of the last, maybe it's here. So there is some also canonical duality that I composed at the beginning. And so there will be also some twist over there. And actually the two twists should cancel. Okay, so this is how we get C, and then actually the hardest part of the article deals with how to deal with B. And so let me remind you, so what do we have to show for every convex chi and B in B minimal? Then I can define U to be B minus the point. And then what I need to show is that pitch B on IUB lower star of sheaf Isoc on U is inside JUB lower shriek of D1 G U. Okay, so this is an instance of this intertwining. Where here maybe I emphasize you only need to do it like one strata at a time, or for the minimal strata. Okay, so let me try to run through you the naive computation again. So I have naive. So maybe let me fix some beta inside of U, right? So this is maybe a point that specializes to B or something of the sort. And then I need to compute this, the image of this functor. But actually, right, just to show that this functor lands on this category, so let me just write it like this. This is contained in JUB shriek of D1 GU, if and only if JBB upper star of pitch naive B I beta lower star is equal to 0. Okay? And so this is happening in Bun G, right? Something lands in this category, Bun GU, if and only if, when I pull back to B, this is 0, right? Because I guess, because B is like the union of U and B. And moreover, B, because I took it to be minimal because B in here is minimal, it means it is open in Bun G, right? And because it's open in Bun G, it is smooth, so it actually commutes with all operations. And actually, that's the reason we care about this induction process and asking for B to be minimal, because we want to use the smoothness of pullback by Bun GB inside of this other set. Okay, so let me try to go through the naive computation. So by the naive, okay, this is just the definition of the naive functor. Then I can try to play exactly the same game. And here you might already get a complaint, because on the previous one I was telling you C star commutes with lower streak. Right? But that's what like a natural transformation of six-functor formalism gives you for free. But here I actually have a lower star. And to commute the lower star with analytification is actually not something that the six-functor formalism gives you for free. So here we have a ULA trick. So essentially I'm trying to do the same thing as before. Okay. Then what was in the naive computation, now I have to commute this guy with this guy, but again, because you're no longer this is no longer guaranteed by a six-functor formalism, you also have to say something meaningful to be able to change them. And this is another thing that we called pro-unipotent base change. But okay, we have this pro-unipotent base change that allows me to change these guys, and now I will get K beta lower star, and I was calling it Q beta upper star of C star, right? And let me remind you what is K beta. K beta was this map over here, right? It's the inclusion of MB into Bun G mer. In this naive computation that we were doing before, we had lower streak, so it was easier, but now we have a lower star, right? So you're kind of like thinking that you have this purple FOSS and you're pushing it to Bun G mer, so the lower star of this purple FOSS contributes to this piece as well, whereas the lower streak doesn't really spread over here. Okay, so with this pro-unipotent base change, we can change those. And finally, okay, I have this computation. Then how do I conclude? I wanted to show that this lands in here, and I told you that to do that, I have to apply an upper star to this and show that this vanishes. So let me go ahead and do that, so I can stick the pullback in the end. And okay, here I can really use base change. To rewrite it as sigma B streak, K beta B lower star of gamma beta B upper star C star. And I just added a lot of maps, right, out of nowhere. So let me just go to the drawing and explain you what happened to these maps. So what happened? I started with something on this point, then I kind of push forward and it can spread a little over here, then I pull it back, and so now I have something here that also spreads a little over here, right? And then from this thing, I'm like lower shrinking all the way over here, right? But then I decided to go on over B, which is this minimal point, and pull it back to explore what happened to it. And so maybe this guy is this. So for example, then what happened? I was here, this spreads over here, you pull, and I ended up pulling back all the way to here, right? I forgot about this part. So I pull it over here and it spreads all the way over here, and that's kind of like what I'm looking at. So I nullify, I pull it to this strata, right? This is this gamma beta B, right? So this is this gamma that has like special generic Newton polygon beta and special Newton polygon B. And then I have this KB beta, and I'm pushing forward. And what is this? I was in this strata already, and then I push it so that it spreads to this piece. And finally, I do that and shrink all the way to Bun G. Right? So that's the computation. And it turns out that this is 0. And this is what we call Henselianity. And the way you should think about it is, whatever this was, in the end, I don't know, there was maybe a lot of mess, but in the end, it was a push forward from something that was concentrated only over here. You push it forward, and then you shrink it. But we already experienced that MB is Henselian towards this point, and the TB is actually Henselian towards this point. So this is why this vanishes. So it seems like I have 7 minutes? Okay. So I guess I managed to mention the 3 main ingredients that go into these computations. I guess as I explained, this intertwining is easy. So this is the easy intertwining, and this is significantly harder intertwining. And to get that intertwining, we kind of like use 3 techniques. Okay, I would say that it's 2 techniques and 1 kind of wiggling with 6 functor formalism. So there's a ULA trick that I'm about to explain right now, and there is some pro-unipotent base change, which is maybe a technique, and there's the 3rd technique that I called, or that we call Henselianity. So I want to say a little word about this, about each of these 3 ingredients. So maybe a ULA trick. You can find this in the paper as proposition 4.1.4. So if f from x to y is a map of perfect Artin Tal stacks, and by this I just mean they are Artin towards the point. The way I define Artin maps, and that is just Artin towards the point. That is P of P, representable, and A is a constructible sheaf. Then C star F lower star of A is the same thing as F lower star diamond of C star A. Okay, so I guess I told you C star in general will not commute with lower push forward, but it actually does if your sheaf is constructible and your stacks are nice enough. And we apply this to restricted Stukas, and somehow we connect it later we connect restricted Stukas to Stukas and then go to Isoc. But essentially the base change formula goes like looking really at kind of finite pieces and starting lower star with a finite piece. Okay, then let me say a word about pro-unipotent base change.
Why is it called
Because maybe, yeah, thanks for asking this question, because I was forgetting to add something, maybe key input. So the key input is that if x to the point is p of p, then A is constructible if and only if A is suave or ULA. And I guess this is a fact we learned from a paper of Peter and Dave, that I think is it attributed to Gaber, this theorem, or? Okay, it's a classical statement now in the literature, but I don't remember who's the original person to prove this. I think Gaber.
I learned a version of this from Liu and Zheng's paper on, electric sphericity traces.
Okay, then we have to ask them where they learned it from. Okay.
So there's no assumption F is proper or anything, like really just any F, right?
Yeah, right. But yeah, it's essentially, you know that you can commute C star with lower shriek, and you kind of express lower star as D of F lower shriek D, and then you start like playing some games.
F lower star will still be constructible, right? Is that the point?
Right. Yeah. Okay. Right. So let me say a word about per-unipotent base change. So already in Xingwen's talk, we were in a context where you have some space and you quotient it by H, and H has to be a nice group that has some presentation like this, where this is finite dimensional, and this is pro-unipotent, meaning it has a filtration, it might be infinite dimensional, but it has a filtration, each of which its graded pieces are isomorphic to A1. And I guess this gives rise to Placid geometry. And it's kind of philosophically saying that the map from X to Y is like smooth enough. And it's smooth enough to be able to commute pullback with like star pullback and star push forward. So you write a diagram like this. Then you'll have identities of the form. And the whole deal about this per-unipotent base change, it's about taking this idea but to the analytic world. And so we need to prove a version where the role of A1 is played by something I want to call B1, which is the canonical compactification of the closed unit ball. There are two reasons this shows up. One that I will explain in a bit if I have time. And the other one is that in this Placid business, one kind of underlying thing that goes through all the proofs is some QCQS property. I mean, A infinity is very infinite dimensional, but it's still QCQS. And this is just not true in the analytic world. Even A1 is not QCQS. And in this per-unipotent base change, there's some QCQS assumptions there, I think, implicitly. The second reason why the compactified unit ball shows up is the following theorem with Ivanov and Zillinger, which is actually analytic Stukas had made a presentation in terms of something I called LG dagger at phi L plus G dagger. where a dagger is a very general construction, taking a pre-stack to a B sheaf, whose our plus points are x of spec r circ. And if you go through the actual definition, if you take A1 and you plug in a dagger to it, then you actually get the compactified unit ball. Okay, so this is why this compactified unit ball naturally shows up, because we have this formula for analytic Stukas that appear in our definition of the functor. Okay, and I guess I'm running very much out of time, so maybe I will not have too much time to discuss Henselianity. And so let me stop here.